I think we can already start, Professor.
Okay. Hello, hello, hello. Let me show my face to you. I am Professor Vladimir Miranda. I am Professor Vladimir Miranda. How are you doing today? Welcome to this new session of our webinar series on energy topics. INESC TEC is promoting this webinar series to allow recent research efforts to be shared with the community, both the academic community, research community, companies, utilities, people interested in these topics. So the objective is not to give tutorials or teaching lessons. It's actually to promote discussion by fostering the awareness of efforts in several domains of the power systems to achieve some progress. And we are very much focused in advancement that may help companies in their business, new forms of business, reinforcing technologies, technological solutions, etc. And this series that started some months ago, that we have one webinar every month, is being very successful in draining a lot of attention. So I'm very grateful for you if you are listening to me. I hope this session will be also interesting. We have two invited speakers. I profit the occasion to remind you that we accept proposals for interesting presentations also. This is not exclusively INESC TEC researcher presentations, and we have in the past presentations from other people. And we have two guests to speak today. And before I introduce the first guest, I will want to remind you that we wish to have as dynamic as possible sessions. So you can ask questions, interrupt, raise your hand, perhaps not like this, but using the tool of the Zoom. Okay? Raise your hand or click in the Q&A to write, to place a written question. And please do not use the chat facility because we are not monitoring the chat facility as a source of questions. So if you want to ask an oral question, we will open the microphone and you can ask them, or please raise your hand to do that, or then write your question on the Q&A. Furthermore, I wish to warn you that during the first presentation, we have some questions prepared as sort of a poll to the audience. So Dr. Luís Guimarães, who is the first presenter, will be interrupting from time to time his presentation, and a poll will be launched with some 1 minute or something to get some answers from the audience. And this will be as interactive as possible. In the end of the presentations, I will come back to you to try to provoke you into some more discussion. And having said this, let me go back to the flow of presentations. So the first speaker is Dr. Luís Guimarães, who is a professor at the Department of Industrial Engineering and Management here in Porto, at the University of Porto. And he is a senior researcher at INESC TEC. And you see that he's not an electrical engineer, which may be an advantage. He has been devoting a lot of research efforts to the maintenance planning based on data, and that's what he is going to explain today. So I will leave the presentation to Dr. Luís Guimarães, who is going to start his presentation right now.
Okay, thank you very much, Professor Vladimir Miranda, and thank you all for being here at this webinar. So as Professor Vladimir said, I'm not an electrical engineer, but I'm almost there, I think, given the amount of projects that I've been doing in topics related to this field. And today, what I have to discuss with you is actually our experience in applying data analytics to the asset management process, and specifically tackling the electricity distribution market. Okay, so I will be sharing some thoughts with you, and also some case studies of projects that we have done in the past to try and to understand how can we explore the value of using data analytics to improve these asset management decisions in the electricity distribution market. Okay, so starting with the motivation, and this is true for the electricity distribution, but it's also true for other industries. Where we are witnessing is a change of the way we operate our assets. And if in the past, many of these asset-intensive industries were kind of stable and predictable, as it was the electricity supply. So the recent trends, and I'm pointing here to some trends in the electricity distribution, such as energy transition, digitalization, electrification, and decentralization. So it's pushing the way we are exploring our assets into different and unknown operation paradigms. Okay, and we are talking about the radical change in the way that we are exploring the assets, which will lead to also a radical change of the way we are approaching maintenance. And this is what I'm going to talk about during this webinar. So we are changing from something that is stable and predictable to something that is decentralized, flexible, with all the impacts that this has into our decision-making process. And of course, this sort of change comes from different factors. Okay, so we have nowadays different market dynamics. We also have new technologies that are disrupting this particular market and others. And we also have, in this context, new regulatory frameworks that are also shaping the way we are using our assets. And I can just, this is not an exhaustive list, but try to put here the major factors that are influencing this change of paradigm that I'm talking about. So the first, of course, is the renewable energy source penetration that is increasing, and we still have targets to increase it further. Of course, with this increase of the renewable energy, we are phasing out the conventional generation. We are also having external factors such as the electrical vehicle penetration, also new technologies like batteries, and of course, new business models that are arising in this electricity distribution, and the regulatory framework that I mentioned that is changing also the way we are defining the service model of this type of companies, okay? And all these factors are, as I said, influencing the way we operate our assets. I give you just a few examples. For instance, the way we are operating our transformers, our lines and cables, also the flexibility between generation and storage. So all this has put an extra pressure in our grid operation, and is changing the ways the different assets become more or less critical. And the impacts are obvious. So we have impacts that are coming from the operation of the grid itself, but I would like to highlight two of the main impacts that are related to the topic that I want to discuss with you. The first one is that these new operating models lead us to situations where the load has become more variable. And this load becoming more variable means that what we have learned in the past from the operation of our assets may not be valid in the future. So we need to continuously know more about our assets and the way they respond to different operating conditions.
Luís, allow me to interrupt you. Mm-hmm. Here is Earth Station, communicate. We have one raised hand. I suppose there's a question. I will allow the attendee to talk and ask the question. Please, the person who has raised the hand, please ask the question. Hello? I have a person identified by E322806 who raised the hand. If the person cannot now answer, okay, Luís, I'm sorry, we will continue.
No problem, no problem. I think there will be also opportunity at the end of the talk to discuss. Yeah,
it's not an attempt to make this dynamic. There was a
but
I answered, but the person is not reacting now.
But we can try again.
Please,
no
yeah,
yes,
continue.
I'll continue. And as I was saying, not only we need to know more about the way that our assets react to different operating conditions, but we also need to make our capital allocation smarter. And when I mean by capital allocation, there is a topic that is not only true for the electricity market, but it's particularly true for this market. That is, we have a fleet of assets that is aging, and it's at some point, and this point is becoming even more closer. It's becoming at the end of their useful life, and this makes the question of how should we invest our money and try to keep the system operating, a question that should be definitely answered. So I'll focus in these two topics: the varying load and the changing of the operation paradigm, and also on this way of trying to better allocate our capital in order to try to avoid this aging of our assets. Of course, we have these challenges, but we also have other sources of opportunities. When I mean by other sources of opportunities, I'm bringing here the data analytics. Okay, so we have witnessed also in the recent years a proliferation of data-related technologies that allow us nowadays to be able to capture more and more data that we can analyze and try to extract value in order to better operate our systems. And some of the, I'd say, buzzwords are here in this slide, but what is interesting for us is that by having this large pool of information, of course, different types of information, from some that are more structured, others that are more unstructured, what we actually get is data related to several dimensions of our assets that we can analyze. For instance, we may install sensors in our assets that will allow us to know more about center parameters of their operation. We also are able to easily collect data on external conditions such as weather conditions with high levels of granularity. We also have been able to collect records about when we did the same maintenance action to a given asset in a more systematic way. And of course, something that is very important also for this market, it is the geospatial information about our assets. And by combining the needs that we saw in the previous slide with these opportunities, this is where I think that data analytics can bring value into the electricity distribution market. So, and this value, of course, is related to the type of answer that we are trying to get out of this type of models. So this chart that I'm exhibiting here, so allow us to have an idea of the type of answers that we might want to answer with our data analytics approach. The first ones that we might be able to answer is, why did some failure in the past happen, and try to leverage all the data that we collect to make some kind of failure correlation or diagnosis of why this particular event happened. Another type of answer that we might have from this data is trying to do projections into the future and try to do something like a prognosis of our assets. of our assets condition, and try to, at the same time, at the time that we are doing this prognosis, try to anticipate which are the risks that we are going to have in the future. And let's say the higher state of maturity that we can have from this data analytics is try to understand, given the information of the past and given our projection, what should we do in order to improve our maintenance policies. And so this, let's say, analytics journey is something that we have been working with several companies, and it's something that we should pursue in this order. So the first one is try to understand what is a failure or what is a fault and try to improve its detection and diagnosis. Afterwards, try to understand what is the remaining useful life of our assets. And at the end, given the previous two, try to define the most efficient maintenance policies. But before I go into detail on these three topics, I would like to understand what is your knowledge on these three areas, and I'd like to have the first question raised. So you have a few moments to answer. So how familiar are we with this concept? So the diagnosis, the prognosis, the remaining useful life, okay, in the context of asset management. I will give you a few minutes to, let's say 1 minute to answer before I go into detail on these three concepts that are very important for the asset management practice.
Very well. In the meanwhile, while we wait for the answers, Luís, please help me in this. I tried to make a projection of your very nice photo and your bio, but I am afraid I made something wrong here in the command of the Zoom. Did actually your slide with your photo, was it projected?
I think not, but
you believe not. So, okay.
don't worry.
Well, they are seeing you alive, but I will, in the appropriate moment, I will correct my failure in operating the Zoom adequately.
Don't worry. We already have the answers to our questions.
You have the answers.
Yeah.
You want to share the answers?
I think everyone is seeing now. I'm not sure. Yes, right?
They are.
They are, right? Okay,
yes.
So most of the answers go into something that I would already expected. That is, okay, we are familiar with the terms, but probably not in the way they are applied in practice. Okay, so some also say that they are new in this field, and others have a deep knowledge about these three concepts. I will try to highlight how we are using these concepts in our past projects. Okay, let me start with one that is more related to what we call the predictive analytics part of this data analytics for asset management, where we are trying to make sense out of the data that we have for our assets, and try to come up with something that we often call the health index. Okay, so a health index is more or less a condition indicator stating if our asset is either in a good state of health or if it's in a poor state of health and needs some type of intervention. Okay, so when we are talking about this type of data analytics to the practice of asset management, we are trying to look into the available data and try to have this condition estimation. And this condition estimation can be done in two separate times. And that's what distinguishes prognosis from diagnosis or failure detection. Okay, so if we look only at the past and we are trying to make some sense out of the data that we have for a particular asset, looking into the past, we're talking about this type of diagnosis in terms of asset management. Once we try to project this condition into the future, we are doing what we call the prognosis. Okay? So let me give you two examples, one regarding the diagnosis and another one regarding the prognosis in the context of the electricity distribution. Okay, the first one, the first one is when we are talking about the condition of, for instance, a power transformer. So imagine a power transformer. One of the most used methods to evaluate this condition is to have what is called the DGA, dissolved gas analysis. So for each one of these particular gases, we are collecting its concentration in the oil present in the power transformer. So imagine that we have readings for a history of a power transformer regarding the readings of these gases in the oil of the power transformer. So by looking at the data of the past records in the power transformer, we can identify by using known algorithms combined with artificial intelligence techniques if a particular power transformer is in a normal condition or not. So the first division here, so if it's a suspected failure or not. And in case we have some indication that it might have some problem, try to use what we call the engineering knowledge methods to extract information out of these gas concentrations that are no more than data that we are collecting from our power transformers, in order to, at the end, define what is a health indicator for the power transformer. And the way we are doing this is that we are combining two worlds that were typically separated, okay? So the physics-based models world, where we have a deep knowledge about the physical-chemical processes that are taking place inside the power transformer, and the world of data-driven models, where we are disregarding all the engineering and we are just believing on the output of our data algorithm. So the way we are doing this, and this is something that we, in our group, we are trying to be expert in doing so, is to combine these two worlds, okay? Not just having a data-driven vision, not just having a physics-based model, but try to combine both in order to have more accurate algorithms. The second one is, instead of doing a diagnosis, like the one we are doing with the readings from the DGA analysis, is try to do something like a prognosis. Out of the same readings, we have the concentration of a chemical that is the 2-fall that would allow us to estimate how long can the power transformer operate without having his paper, his isolation paper, the severely degraded. So they are well known, again, engineering knowledge methods regarding the way that the paper degrades over time. But in this case, again, we combine these well-known engineering knowledge methods with artificial intelligence techniques in order to, on top of these engineering knowledge methods, introduce the effects of explanatory variables, such as the technology of the power transformer, the quality of the oil, and in particular, as I said in the beginning, the way that that particular power transformer was operated through time. And this has a huge impact in the remaining useful life of this particular asset. So this was the, let's say, the field of the, let's say, more predictive analytics area. Once we have the idea of the condition of our assets, the next step is to take action and understand what can be done to prevent some failure to occur. And in this area, we start talking about what we call the prescriptive analytics. And we are trying to recommend actions that should be done to mitigate potential effects of a failure. And we can do something like inspections, repairs, replacements, wherever, depending on the operation. But before I go into detail also in this area of maintenance optimization, I would like to do the second question and understand, okay, what type of KPIs should we include in this maintenance optimization, okay? Should we include just cost? Should we be concerned about safety, risk, all of the above? I will give you also a few seconds to answer. While you answer, let me say that, of course, this was also expected. I think this was more expected than the previous one, but of course, depending on the problem, of course, we should look at all the above. In the past, depending on the application, maintenance was mainly concerned with a single objective, either cost, if you wish to operate the system as most cost efficient as possible, or in the other extreme, you are very concerned about safety and you are trying to define your maintenance plans in order that safety was not at all in risk. What we actually have done, and the way we should look at this problem, is try to have a multi-objective approach. And when we are talking about multi-objectives, that there is an intrinsic trade-off between these two dimensions. So the cost dimension and the risk dimension. And when we talk about optimizing maintenance policies, actually what we are trying to define is at which point of this trade-off we want to fit. Because we can either have a very cost-efficient maintenance policy, but that is somehow more risky, or we have low risk, but with a high cost of our maintenance. So by setting the point where we want to be in this trade-off, you are trying to evaluate both indicators at the same time. And let me also give you an example to make it more tangible, this explanation. So imagine that we are trying to define the maintenance policy. In this particular case, is the inspection policy of a critical gas distribution infrastructure, that is the PRM, that is responsible to control the pressure in the distribution lines. So we can have a risk-based maintenance policy trading off these two aspects, okay? One is the consequences of our failure, okay? So it's kind of the risk. And for these consequences of our failure, we can talk about different indicators such as the gas that is not supplied if something happens, the number of customers that are going to be affected by a given event, also potential material damage that we might have from this failure, and potential fatalities that often is a very an indicator that concerns a lot this type of companies. And on the other end, we can cross these consequences with the probability of something happen, okay? And we can also, doing some data analytics, try to classify the probability of some event to happen into high, medium, or low. And at the end, we can define an inspection policy based on a risk matrix, such as this one, for example, that will allow us to explore the trade-off that I mentioned previously. Okay, so we are trying to balance between the risk, but also the cost of doing some type of maintenance policy. Okay, so just for your indication, in this particular application, we could have the same cost expenditure, so we are not using one more euro to define the maintenance policy, but by reducing the risk into more than 60%. And just to conclude, because I think that my time is already running out, I like to say that with this journey that I've been presenting to you, so the first is trying to evaluate the condition of our assets, first from a diagnosis perspective, and then from a prognosis perspective, and then going into a definition of a more efficient maintenance policy. What this can enable is to companies to do things like improving their quality of service without improving their expenditure. Avoid And this is a very important point. So avoid unproductive actions such as unproductive inspection in not risky assets, trading off not only the risk and cost that I presented before, but also trading off this perspective of having a better quality of service and the amount that I need to invest in my assets. And also, it's something that is very important, have an idea of how much does this maintenance of my infrastructure is going to cost in the future, and try to come up with more sustainable investment plans in such a way that we kind of stabilize our investment policy, and we don't need to go into peaks to renew our fleets. So thank you very much. I'm open for questions.
Professor, you need to unmute.
To unmute. Hello. Very well. We have we are moving to questions. I have a raised hand. Yes. So let me give which I'm trying to find out who is the attendee that has a raised hand to allow this person to.
He is already on board.
Who is, I cannot find Joanna.
Well, yeah,
but
yeah.
If the person, if you can give the words to the microphone to this person, please ask your
already
question.
did.
Hello, can you hear me?
Yes, yes. Hello.
Okay, thank you. My name is João Campos. I work at a small company, United, and I understood that when it comes to transformers, okay, you are basically looking at the gas concentration around that is being delivered, so to say, according to time. And from that, you try to estimate how long that transformer has to live and its current status, so to say. That's what I understood. My point, what I would like to know is two things. First, the cost, in the sense that how much did it cost for you to produce or to buy a sensor to measure that thing, first, and secondly, if the second thing I would like to have your opinion on is, do you have another variable to check the transformer status? For example, if looking at the gas concentration was not an option, okay, what would you look out for? Mm-hmm. These are the two things that I would like to have your opinion about.
Mm-hmm. So thank you, Jean, for a very interesting question. Let me say to you that this project in particular, all the readings were not based on sensors. Okay. They were made on samples that were collected from power transformer periodically. So you would go to the power transformer, collect a sample of the oil, and then analyze it in a laboratory and get the results. Okay, so this has been done in the past for a couple of years. And at the end, what we have is let's say, historical register or records of the gas evolution inside each one of the power transformers. So this was not actually done with sensors, okay? It was with a less technological environment, let's say.
Okay.
But it was a very interesting question because at the end, so this project that we did and this analysis that we could provide based on these concentrations allow us to understand a couple of things regarding the evolution of the concentrations of the different gases. Mm-hmm. One was that not all gases conceal the same level of information. So some were more important than others. And this was actually an important output that could help us define which type of sensor do we need to buy, because the sensors have different technical properties and they are measured different number of gases. Okay, so in total we can measure, I'm not going here into much detail, but in total we can measure around 9 gases, and we realize that 5 of them conceal the most of the information. So we could go to cheaper, let's say, sensors that do not need to monitor that amount of different gases concentrations. Also, as you mentioned, this was not the only indicator that we could get out of this analysis. This is, and that's why I use it as an example. This is one of the most, let's say, consensual way of evaluating the condition of a power transformer, but we can also evaluate the condition from, let's say, for instance, the perspective of the oil quality, okay? Not just the power transformer itself, but also the quality of the oil that could give us or could point us also in terms of the maintenance action that should be done. And of course, we can also have the readings from the electrical measurements. But at the point we didn't go into that into those type of indicators, because actually the data that could be provided was not that extensive for the portfolio of power transformers that was under study, and at the end we concluded that the DGA analysis was more, let's say, a more even way of evaluating the different power transformers.
Okay, thank you very much.
Thank you.
I will make a comment using my privilege as moderator, which is the following. For the solid gas analysis, one of the best indications come from ratios between gases, not from the presence of a gas itself in dissolved oil. There is a natural aging of the asset, of the transformer, and then incipient faults may cause accelerated aging and even announce an imminent disruption of the machine. And in these cases, maintenance is sort of catastrophic. It means removing the transformer, shipping it to a factory to be reconditioned and repaired even. But this possibility of using sensors adds a lot of value to the business of selling transformers, because if you think of it, distribution transformers are almost like commodities today. And so the companies sell transformers, the manufacturers sell transformers competing basically on price. So if you can offer together with the transformer some service like monitoring the aging, etc., and this implies having some sensors added to transformer and remote monitoring, keeping models, analyzing, then this adds value to the business of transformer selling and adds value to the company that holds the transformers. So this is a very, very widespread problem in many companies that I met in the world, but there is no other way besides sensors than just collect a sample and send to a laboratory and wait for months for the answer. Thank you very much.
Professor Wagner, let me just add one final comment based on what you had just said. That is, of course, that is true. If you are going to buy a new transformer, you're going to have it sensorized in the best possible way. But when you have a portfolio of aging transformers, it's also very important to understand which should be the ones that you are going to start collecting data based on sensors. So you can have kind of a priority list of which are the power transformers that should be first sensorized in such a way that we can even avoid these catastrophic failures, as you mentioned.
Absolutely, I agree totally. Okay, so we can open the microphone to some more questions. Because if there aren't any questions, we will move to the second speaker. At the present moment, I don't see any other questions. So let me thank Luís for his aperitif presentation oh, I have another question. Joanna, please, there's another hand raising.
Yes, the permission has already been given.
Okay, Antonio Carapatoso, welcome.
Hi, hope you can hear me. I have just one question. We are talking about transformers, but in the distribution network, there are basically two kinds of transformers. Power transformers that are located in primary substations. And for instance, in EDP, in the Portuguese network, there are a few hundred transformers that are located in also a few hundred primary substations. And there are several tens of thousands of distribution transformers that are basically smaller transformers that they are essentially the same, but they have a different size. The point is that to not concern the secondary substations and the devices and assets that are located there, they are essentially the DSO basically follows a fit and forget approach. That means install the devices and know nothing about what is going on. And the point is that how do you plan to gather data from those devices?
Thank you, Antonio. It's also a very interesting question because so this one that's as you correctly say, this approach was more tailored to the power transformers in the substations, in primary substations. In fact, after this study on this type of power transformers, we studied the ones that you are mentioning, secondary ones that are responsible to the medium voltage to low voltage transformation. And in that particular case, we choose a completely different approach. So for those, we are trying to identify a couple of variables, identifying which are the factors that are influencing their reliability. Essentially because they do what you say, they do a fit and forget strategy, but they should be able to plan so they reserve equipment. So they have to do this type of fit and forget, they should have to have reserves of those power transformers ready so that when particular failure occurs, you have a backup power transformer. So you still need this type of data analytics approach to allow you to have better estimations of how many power transformers should you have in reserve in order to solve the problem. So, but this is in the short term, because of course in the long term, something that we have been discussing for the previous power transformers, you can also discuss for these smaller ones. Although at the end, it would be a trade-off in terms of cost benefit that we can have by installing more technology in these smaller transformers versus the benefit that we can extract from that particular extra data collection. But it's still an open question. I don't have an answer for you. I wish I had.
Thank you very much.
Thank you very much. I think we need to move to the second speaker. I just say to finalize that, my friends, this talk is one of many that opens a view over what I try to call Power Systems 4.0, which is moving into a standard in the industry of power, closer to the standard of in manufacturing industry called 4.0 using IoT, etc., etc. Because the pervasive use of sensing information from the assets is the way how we can then apply intelligent models to do prognosis, etc., etc. And I see in the power industry, including in transformers, this movement going on. I have experience, for instance, in some areas in Brazil, distribution transformers having been overloaded for excessive time without any kind of sensing. This causes accelerated aging and then problems, as you can imagine. This will, today we have the means not only of sensor but of communication and real-time sensing. We have the means to do it cheap, especially in all areas where smart grids concepts are expanding. And we actually have to put something near the transformers to concentrate information on consumers and on the transformer itself. So this is the good base for progressing with these solutions. Thank you very much, Luís. I will move the screen to the other speaker, Gil Sampaio. Let me see if I can now correctly share my screen. Screen to share. This I must do, and then, okay, here. Now, this was the nice photo I wanted to show you of Luís. You can see also his resume there, and then we move into Gil Sampaio. Gil is going to share with us some details and some information on how his team has tackled the problem of state estimation specifically in low voltage distribution systems and experiencing some European projects. And he's finishing his PhD degree in sustainable energy systems in University of Porto and INESC TEC. And I am giving the screen to him. So let's stop sharing. And Gil, the microphone is yours, please.
Hello, everyone. I would like to start this presentation talking for a few moments about what state estimation is, in particular, its application to power systems. So a state estimator is a tool used by grid operators to determine the most likely state of the system, considering that measurements are naturally affected by errors or are even missing. In this slide, we have represented some of the function blocks of a commercial solution. Measurements are gathered by measuring devices spread along the grid and are sent to the control center. A first data filtering is usually used to remove data that is clearly erroneous. The topology processor is in charge of building an updated but simpler representation of the network. Then the data is analyzed in terms of observability. Only a full observability of the network is accepted in traditional approaches. So if measurements are missing, the load allocation tool is used to provide an initial estimation of those missing quantities. Then, while the state estimator is running, some of the measurements can be found to be erroneous, which may lead to the remotion of those measurements from the dataset. And finally, we get an improved image of the network, which is sent to the operator. And this process can run every few seconds, updating each time the system state. Mathematically, the problem is formulated as follows. For each measurement, there is a function that quantifies quantifies that measurement in respect to the state variable. Usually, we use as state variables the voltages in polar form. Therefore, we want to find the value of these state variables that minimize the error between real and estimated values. We can use a weighted least square formulation, and then we can apply the Gauss-Newton method to solve this minimization problem. This is the most typical and traditional approach to the state estimation problem. However, power systems are evolving and different approaches may be needed. There are three main trends that will bring new challenges in power systems: electrification, decentralization, and digitalization. The use of fossil fuels will continue to decrease as more end users are powered by electricity. The presence of distributed resources, particularly renewables, will continue to grow, not only with the objective of reducing pollutant emissions, but also, for instance, to increase the security of supply. Finally, a major trend is the digitalization of the grid, because we now have technology that support a better control and allow a more efficient operation. So all this can bring huge benefits, but of course there are a number of challenges that must be addressed. Perhaps one of the parts of the grid that face more challenges is the low voltage. This can be explained by the growing presence of electric vehicles, microgeneration, demand-side management strategies, and so on. But also because the low voltage grid was neglected in the past in terms of monitoring and control due to its relative passive behavior. So if we look to the most low voltage grids, instead of this, we find this, an incorrect or even inexistent characterization of the assets. So, well, the great news is that smart meters are producing a lot of data. And maybe it's possible to take advantage of that. In fact, if we look to the variation of the voltage during a few days, it is very clear that there are patterns. And when we analyze the voltage correlation between two distinct points of the same network, we see that there is correlation, even when those points belong to different phases. So we came up with a state estimator that relies purely on big data. In general terms, it works this way. At the current time, it determines the current voltages using some real-time information, measurements that are gathered from a subset of meters, and uses historical data. So we must assume that these kind of devices are present in the network. Here in more detail, looking at the timeline, we have a few smart meters that communicated recently, and all the others that communicated only 24 hours, communicate only every 24 hours. And we want to estimate the voltage at one point of the grid that does not have real-time metering. We only know its past. So we build a set of explanatory variables with information that we do know. We can use real-time measurements, weather data, historical measurements, and so on. Then we build the same set of explanatory variables for each past occurrence of that point. With this, we will measure the similarity of between the set of explanatory variables against the past, and the most similar will have a higher weight in the smoothing process, which we calculate here. So the innovations of this approach are the following. Only a subset of smart meters need to communicate their measurements in real time. The estimations are provided in the form of conditional quantiles expressing the uncertainty involved in the estimation. Parts of the grid could not be monitored. It's not a requirement, the full observability as it is in the traditional methods. Electrical characteristics of the equipment are not used at all. And additional variables that have impact on the measurements that we are trying to estimate can be included, like weather data, market signals, calendar, and so on. Regarding the smoothing process that I mentioned before, each estimated voltage is a weighted average of the most similar events in the past. And the similarity, which is translated by a weight, is measured considering the distance between the current instant and the past observation, a bandwidth that defines the observation window, and a function that transforms distances into weights. This distance used in this work was the absolute distance. The selection window is a percentage of the range of distances. And finally, the expression that converts the distances into weights, which is a negative exponential, and that attributes higher weight to the most similar snapshots. The parameters in red, the percentage of the range of distance and the decaying parameter need to be tuned so the estimations are more accurate. In order to provide a probabilistic representation of the uncertainty, we use the kernel density estimation, which basically expresses the probability density function of a variable by smoothing out individual observations. The so-called smoothing bandwidth, this parameter here, needs to be tuned. If the value is too low, there will be a lot of peaks in the final PDF. On the other hand, if the value is too high, important features may be smoothed out. Then we include this estimation in the previous smoothing expression, and we got this final expression to determine the voltages. As I told you, there are parameters that need to be optimized. The tuning of these parameters occurs in two different stages. An evolutionary particle swarm optimization is used every 24 hours when the historical data is updated. And the fine-tuning of the same parameters is performed every time a state estimation is required using a dynamic simplex method. This means that the estimator is continuously adapting to the time-varying changes in the patterns. Now, I would like to show you some of the results we obtained for the 33 bus system, considering different levels of PV integration. And as explanatory variables, we use the time and the day of the week, the radiance, which is particularly important due to the presence of microgeneration. We considered to have real-time measurements in the secondary substation and in the beginning of each feeder. Also, historical data, namely the voltage measurements T-24 and T-168. To determine the quality of the estimations, we had to define some metrics. The deterministic state estimations were compared against an autoencoder, from which we measure the mean absolute error and the maximum absolute deviation. In regards to probabilistic estimations, we measured the calibration and the sharpness of the estimated PDF. Then we built a quantile score that expresses these two metrics, and that was used as a criterion to optimize the smoothing bandwidth. As I said, we used an autoencoder to compare the deterministic state estimations. We put our state estimator against that autoencoder using during a simulation comprising 2,500 simulations. Both performed well, but the low voltage state estimator was always better than the autoencoder. Moreover, the autoencoder requires a heavy training stage, which resulted in a simulation that took more than 1 hour, while the state estimator only needed 86 seconds. In the chart is just an example, but we have a snapshot of the probability results for one of the nodes of the network, only to show you the conditional intervals that are output by the tool. Here we can see the representation of the sharpness and the calibration of the estimated density, proving the good capacity of the method to estimate the uncertainty. This state estimator was tested under real exploration conditions, which is very interesting. The InteGrid project was an initiative funded by the European Commission, where we had the opportunity of demonstrating with real grids a number of tools, including this state estimator. In the case of the low voltage network, it was built a framework to monitor and control the low voltage network with flexibility negotiated under market rules. The role of the state estimator here was providing the most likely state of the network to the grid operator and to the control algorithm, which would act if any under or over voltage was found. Here we have some more details about the demonstration sites. There were 3 low voltage grids, 2 in Valverde and 1 in Alcochete, with more than 370 clients. As I said, the state estimator would provide the most recent state of each grid to the control tool to evaluate any possible under or over voltages, and would send it as well to Power On Advantage of General Electric, which was installed at the control center for visualization purposes. And it should be noted that only 10% of all the measuring devices were required to have the capability of communicating in real time, and all the others communicated by the end of the day. And this is a very important characteristic because it reduces considerably the burden over the communications infrastructure. I have also here some results from these demonstrators along with some metrics. Visually, it's clear that the estimated quantities are quite close to the real values. And it's particularly interesting to see that even in the case of active powers, which are known to be extremely different to forecasts in the low voltage, the algorithm performed quite good. So to conclude, the low voltage grid is evolving and for sure requires innovative approaches. We already know that some methodologies do not work here, so we must explore what we have, and in this sense, big data seems to be an opportunity. And a good example is this state estimator that I've just presented, which has proven its value in real conditions. Nevertheless, we plan to continue improving it, namely regarding its performance under extreme or rare events. And that's it. Thank you.
Thank you very much, Jill. Thank you. I hope my microphone is unmuted and everybody is listening. So we had the presentation of some results from field tests. Are you allowed to elaborate what was the area of tests or in which country, for which company, etc.? Are you allowed to say that, or is it confidential information?
No, I don't think so. I hope not. It was in Portugal, 2 secondary substations in Valverde, and 1 secondary substation in Alcochete.
So that's for EDP.
Yes, they belong to the EDP. Yes.
Well, very well. So now I'm inviting everybody to ask questions. You can use the Q&A facility and write your questions, or you can raise your hand and we will give you the microphone. Meanwhile, while we wait for some question,
I have already gave permission, Professor.
Yeah, okay.
So a participant.
Okay, João Campos, I believe.
Yes, it's me again.
Please.
Sorry for the inconvenience.
No inconvenience. On the contrary, you are contributing to a dynamic session, so we are grateful.
Thank you. Let me ask you, make a few comments, and I would like to also to make a question, of course. When you talk about state estimation, you have first slide talking about the challenges of the LV network, electrification, decentralization, digitalization, etc., and so forth. But when you talk about state estimation, I am assuming that you are basically monitoring the PV production. So I'm assuming that among the information that you extract from the state estimation, you extract information on which smart meters have a PV associated with them. That's what I understood. I don't know if it is correct. The second thing is you somehow seem to assume in your problem that you already know that a specific network has a PV. For example, you seem already to know that the networks in Valverde and Alcochete already have PVs. But does your method allow you to detect that first you have PVs there and only after apply the state estimation? I don't know. That's what I would like.
Okay. Sure. If you allow me to reply. I'm afraid I don't understand why you believe that the method is particularly suited to networks with photovoltaics, because it's not the case. We used photovoltaics in these demonstrations because it's a resource that exists and that can create problems. But we know that other devices can bring complications, and in the future, perhaps the spread of electrical vehicles will be much bigger problem than the photovoltaics. What the method does, and it has nothing to do with the kind of assets that are in the network, it tells to the operator what is the most likely voltage in every node of the network, regardless of the assets that exist there.
And by comparing with the actual measures, you are able to know whether something is wrong or not.
No, not exactly. What it does is I will try to explain in a simpler way. One of the assumptions is that all the customers, or most of them, have a smart meter. And that smart meter sends measurements, or gathers measurements every 15 minutes, but only communicates those measurements every 24 hours. So what happens is that during that window, the operator doesn't know what is going on the network. Only after receiving that historical data, he knows that there was an under voltage or over voltage. So what we propose is that by installing only about 10% of smart meters with GPRS, which can communicate in real time, the operator is capable of estimating the voltages for all of the nodes of the network. That's our proposition.
Okay, thank you very much. I have a much clearer picture about it now. Thank you.
Thank you.
Very well. Maybe we have other questions. We have on the Q&A, we have one question from João Dionísio, who asks, was a paper written for your work that we can access? I would like to go a bit more in depth into your work, if possible. Please, can you answer this question, Gilles?
Yes,
do you
Professor.
Have a paper
yes,
on this?
Yes, it was published a conference paper in 2018 in Dublin, the PSCC, and I can find a way of sharing it somehow. I don't know.
Yes, if João Dionísio would like to write to you or to the organization of the webinar, we can forward the email to you, and then you can reply sending the paper. sending a copy. Don't send the paper, send a copy. Otherwise, you will be without papers in your CV. Then we have a question. I hope it's answered. I would like there's another question from a participant just identified by E322806. That's a long name. And the question is, how were the 10% real-time meters chosen? Location, etc. How were they chosen?
Well, it's a very curious question, because the answer is that it was somehow random. I mean, we noticed that it worked. The method worked very well with about 10%, regardless of the location of the meters. But in that sense, we can say that if we look at it further on the subject, maybe we could even reduce even more the number of devices that need that capability by choosing an optimal location. But in the case of this work and the application that we used in the live demos, they were randomly chosen.
Very well. I hope this is answered. I still see a hand raised, but I don't know if it was related to the previous question from João OB. Do you want to ask another question, João?
Me? No, I thought I lowered your hand.
Okay.
My hand.
Okay, I will lower your hand. Let me still say something, perhaps a mix of question and answer to Gilles. This is an important, these models are important, and this presentation, in my view, is specifically important because it is based on actual field experiments. And this makes it valuable as it is traditional in the work of INESC TEC, because we are not just producing academic theoretical work. I can share with you that my personal opinion from my professional experience, if you want, is that the future will be in the cohabitation of different types of sensors with different types of frequency measuring. The frequency of capturing information from your model, how was it, Gilles? Every 10 minutes? How was it
15.
For 15?
15.
Every 15 minutes. For some purposes, this is totally satisfactory, but there may be reasons in some cases that we would need a higher frequency, and we have tested also in other places and not related to these experiments, something that we are working very strongly towards, which is cohabitation of different layers of frequency of measurements, because you could add information from past data. You could add information also from one PMU. And the PMUs in low voltage, you may ask, yes, the prices of PMUs are coming down at a pace that would look like what happened to photovoltaics or batteries. So very soon you will have also PMU information devices available, not to put a PMU at every node of the low voltage, but this information is a much higher frequency of collecting data will add extreme value to the estimating algorithms that we are implementing. And this hybrid approach, in my view, it's the correct approach, because in the past, some years ago, especially in China, where they promoted, actually pioneered the use of PMUs. They argued for some time that you could forget about all other devices because PMU estimation will be enough. We now know that this is not true. And it is not a good solution for the companies to just throw out all the devices that they have and replace by PMUs. That's also not a good solution. So the other important thing that I would like to comment is that these methods allow also estimating voltage at nodes where you have no sensor. This is very important, okay? Because one of the objectives is not to put sensors all over the low voltage network. There will not be money to pay for that. But it is very important to estimate signals like voltage and current and other signals that you want. And you can move later into dynamic signals when you have things like distributed small wind generation and microgrid working in isolated mode, etc. You would like also to collect dynamic data. So this is the future, I believe. Now we have some comments, and there is another question from Pedro Benedicto. I don't know if he's from Brazil, Spain, Colombia, or just added a C to his name. But the question is there any rule of thumb to know how many measurement points are needed for this estimation to be useful? Okay, I think the doubt is about the level of monitorization, mean the redundancy or whatever you want to call it, needed at low voltage for this state estimation. So this is a good question, Gilles.
Yes, it is. And unfortunately, there is no rule, not even a rule of thumb. And what works in one grid may not work in another different. But the tests that we conducted were not in the sense of trying to optimize the location or the number of measuring devices. So I cannot answer, but for sure there is it can be investigated, and for sure it will be useful to know how can we know the number and the location of the measuring devices, that the minimum that are necessary to provide accurate estimations. But I don't know the answer.
Well, the question is interesting. I would say that for every case, it is very easy to study and find out a compromise between the number and placement of measurements and the accuracy in predictions that you get. The idea of having a rule of thumb is interesting in the sense of practical engineering, to have a global idea, although that will depend on the characteristic of the network. We have here also a question by Julio Massignan from Brazil directly. If you are a supporter of Palmeiras, congratulations for winning the South American Cup of football. And the questions are, how does the method perform for reactive power estimation? And the second, are you exploring the possibility to estimate topology with historical data? So first, reactive power.
And I don't know the answer, but I believe that it will perform very poorly because reactive power at the level of consumption, low voltage consumption, follows as a very random behavior, and we didn't try to estimate it first because it's not so relevant as active power. But I believe that it will be very, very difficult to have good results. Regarding the topology, we did not explore the topology estimation during the development of the state estimator, but currently we are developing we are still developing a control tool for the low voltage network based purely on data. And we are building sensitivity factors, which translate how changing the power in one point affects the voltage in the rest of the network. And by doing that, we found out that those sensitivity factors give us very, very interesting information, like they can tell you if the 2 points belong to the same phase, and even can tell you the proximity of between 2 points, the relative proximity. So we are looking at it, and maybe we can do something about it, but right now we still don't have anything.
Thank you. Thank you. Well, I just want to remind that this is about for low voltage. Most networks are radial. Okay, and,
yes.
and this causes other constraints to be to the estimation. But I would say that there is another problem that has not been in any question from the audience, which is the following. How can these methods serve to estimate parameters of the lines of the system? Because if the parameters are unknown are uncertain at high voltage network, in low voltage, I am absolutely sure that the degree of uncertainty in the resistance length, whatever of the lines, is to a very high degree. Plus,
they don't exist.
Plus, it must be a three-phase model. Okay, a three-phase unbalanced process. Okay, but my feeling is that these methods will serve in the future also to estimate and correct parameters. And I think we have someone still wishing to ask a question, which I don't know who he is, but
it's Antonio.
Please.
Yeah, sorry to interrupt again. Just one question about the low voltage network. The reconfigurations on the low voltage network are normally limited, but in urban environments, that is not really true, because the same network may be fed by different secondary substations. But on the other side, on the medium voltage network, the network reconfiguration, either because of accidents or because of maintenance purposes, are quite common. How does the state estimator behave in if there are network reconfigurations?
Well, that's a very good question, because it is based on historical data, and if something changes, the historical data may get invalid. And if we consider that we are also using measurements at the level of the secondary substation, if the secondary substation changes, or there is any kind of reconfiguration, we may need to gather sufficient new historical data to train again the model and be able to provide accurate estimation. So it's not very suitable to grids that change a lot.
Okay, thank you.
Okay, thank you very much. I think we can come to a closure. Thank you. I thank the panelists, and I also thank the audience. And we will have in the next month a new webinar. I hope you can spread the word. And also we are eager to receive suggestions on how to improve the dynamics of these webinars and on topics that would be of interest to the community. Thank you, Luís. Thank you, Gil. Thank you, Joanna, for providing this maestro qualities in conducting the whole interface. And thank you to the audience. Have a nice day, have a nice week, have a nice month until our next webinar. In the name of INESC TEC and everybody, thank you so much.